Mathematical equation. In other words, there's a spot height, where does the contour come between them and what distance, and I'll show you that on the whiteboard as well. And then we'll go on to what we call design contours. Design contours are basically where you take a platform, the ground going up to the business school, for example, not the business school, it's called the IBM building now. The ground going up that way. Most of you have walked along the top road, I assume, to the gym or something like that, like something I haven't done for a long time. Perhaps you've looked down at the slope going down to the wetlands. Imagine if I was to put a tennis court there and just rested a platform of, say, 10 metres by 10 metres into the ground at a certain level. Some of it will be dug into the bank, and some of it will need to be supported by some fill. Okay, so that's the calculations we'll be doing on the board here graphically, and we'll show what they look like in plan view, what that would look like in plan view. In order to help you a little bit more tonight in your lab class, you'll have quite a bit of time to carry on with your assignment, but before we do that, in AutoCAD I will have a little class example to do for you to have a go at, which will be similar to the one that I do on the board. And then, as a bit of a surprise, I'll show you a 3D model of it, and you'll get to see it sort of develop from a 2D image to a 3D image. And some students go, whoa, I understand that now, I know what's going on. You will need to know how to do design contours for assignment 2. So you'll notice there it says your proposed plan, assignment 2. So for some of you, that's sort of miles away. 321st, a wedding, a funeral, something else. But for others, okay, I'll put that in my bank, I'll put it there, and I'll go and revise that a few weeks before we start assignment 2. And then we'll have an opportunity for me to walk around your work, and I'll be able to say yes or no to your hatching. 38 students, perhaps 1 or 2 questions each as I walk around. I tend to get 1 or 2 that try to dominate with about 20 questions. While we're on that topic, as far as things go, for those that weren't here last week, I'm a little bit different to most of the other lecturers. I don't sit in my office from 8 till 5, waiting for Sheldon to start knocking on the door. Penny. And then at 5 o'clock I don't talk to you again to 8 o'clock in the morning. I tend to be fairly open for most of the time when I'm near a computer. So often you'll get quite a surprise when you fire a question through to me. Some of you have already done that. Okay, but what I can't do is what a degree student asked me to do. Please meet me in your office for an hour to show me how to put the title block in and set the viewport. Now for a start, the viewport is last year's learning outcomes. Got a pretty set of notes on how to do that. Secondly, the title block was demonstrated in week 1. I don't keep demonstrating. A lot of you took videos. Great chance to make some money out of it. If you want to send me a link to YouTube of that video, I'm happy to put that on Moodle as well. The idea is to encourage you to come to class. Those that come to class have a very good chance of passing this course. So, I will answer screenshots within reason. For example, the title block itself on both drawings is worth 1 mark each drawing. So that's the long section in the plan. Now it has to be perfect. And you can't say, oh Roger, when you were doing your demonstration, you inserted the title block on layer 0. You should know not to insert the title block on layer 0 from last semester. You don't do a title block on layer 0, right? So that's the sort of thing you've got to be careful of. You've got to bring that through from last year's notes. There's also a lot of other things from last year's notes. For example, the pipe is in the ground. So therefore, according to technical literacy notes week 2, anything in the ground or the background is dashed. Right?
Yep.
The pipe is circular. So therefore anything circular has got a centre line. Now I shouldn't have to tell you that. It should be a direct reference from last semester. But I get a lot of students going, it's not fair, you didn't tell us what line types to use for that. So, there's a lot of back referencing and forward reference. It's like surveying. If you're doing surveying, you can't just learn how to do levelling and then the next year rock up and go, hey, can you teach us how to do levelling again? And you've gone on to precise levelling, which was what I got taught, and it was just a different level altogether. We did that on a dam, by the way, to make sure it wasn't going to move. Okay, so this week's notes we'll start with, and then we'll rock and roll into contours, and then I'll do some examples on the board. This evening we will go right through to, I will take my 10 minutes every hour break at the end. I have to leave around the 22:30 mark, so but you're entitled to stay there as long as you like. The lab will be open until 9 or 10 o'clock at night, if that's what you want to do. Okay. So going to week 2 notes, you'll notice that every time we start the notes, we start again from week 1, and I just add a wee bit more on. And the reason is every now and then as I'm rolling through, I just do some reminders. And a reminder to this class is that please only hand in 2019 files. If you hand in a file from your home computer, which is say 218, there is a chance bits will be missing. It's not up to me to go to your house to look at your screen to make sure that everything's right and then mark your work. If you hand it to me and I open it in 219, that's what I mark for all of you. Flat line. I mark by, not by name, I mark by student ID, so I just work my way through everybody's drawing marking with a very even and fair mark. I'm quite hard, but I'm very fair about the way I mark. So one way around that is to maybe bring your work into Unitech and open it on 219 and just check things to make sure you're happy. Or another way around it is to go to the student website on Autodesk and download 219. Don't download 220, it's due out shortly. They'll just be using you as guinea pigs and I won't be able to open it, so we will have a problem. Problems generally end up in students losing half a mark, all right? What was I going to say? Yeah, it's not up to me to tell you how to download from the Autodesk website. Usually I get students that are all excited, they've got their $1,000 laptop and they're all excited and they want me to go around in my pyjamas and download 2019. It doesn't happen. Okay, so if you can't do it, ask somebody that's already done it. They may be able to help you. Autodesk also has a question and answer as well. So you can, they're pretty good apparently. If you're at the right American time, you can usually get a fairly good answer out of them. We briefly covered on a number of things, but the most important thing was this. And I've had students ask me about the bush, about the house or structures, about the swamp. We covered all this last week in quite a lot of detail. If it doesn't look what I've asked for there, then it will be marked down. As far as the fill and cut batters go today, we're going to be showing you those. I did say last week they are for assignment 2, not 1. In fact, there are some things that if you put on assignment 1, you will lose marks, i.e. flags, section flags. That can only go on a proposed plan, not basically an existing plan. Existing plans are pretty much what surveyors produce. It's pretty much what's on site as you see it, with an occasional thing that might be proposed. The other thing that's happened in email land is students have gone, oh, I've got these fantastic trees. When I put them into my drawing, nothing fits into the viewport. all sorts of questions like that. Well, I did say you are allowed to take trees off the internet, but I also said be careful. There are 3D trees. You insert a 3D tree, and you think looking down on it, the tree is right beside everything else, but in the view, in reality, the tree might be inserted at 0 ground level, and the rest might be at 50 metres, or the other way around, the trees come in at 100 metres high. So just be careful. You're creating issues that you don't need to create in AutoCAD. I did say just a simple tree will suffice. Big word for me. Will be fine. Okay, as long as it is pretty close to the same diameter as the trees that are there. Same with North Points. There's no need to do particularly wonderfully fantastic North Point, just as long as it's pointing the right way, it's in the viewport, and the end isn't too big. Actually, the whole North Point isn't too big. We covered locality plan, we covered all the things that should be on your existing site plan. If you're struggling to know what to do, go to section 1.21 and make sure that a lot of the stuff on the plan is starting to look like the things that it's covered in here. Hopefully by the time we all go into our lab tonight, you guys would have made a pretty good start on this, and you'd be all ready to start looking at the contours. Which leads us into this week's notes. A little bit hard on here actually. It was much better with the degree class yesterday because we could look out the window towards the hub, and if you think to what that looks like, it's quite flat, right? The hardest design that you'll ever have to do if you ever end up working in civil engineering is flat design. That's why when the earthquake hit Christchurch, it couldn't have been a worse place. Most earthquakes happen in hilly country, in mountainous countries. This happened on very, very flat land. So underneath the ground, the pipes are all going up and down, the land's going up and down, and everything in Christchurch had been designed for perfect drainage, perfect sewage, and all of a sudden, it's all changed. So that's why the rebuild was huge. It was a big job. There are pipes under the ground have got to be a certain distance so trucks don't squash them. There has to be enough fall to get it into the ocean. Everything's flat. It was a nightmare doing the design of Christchurch. And because of that, they needed contours down to very small intervals, sometimes 50 mil in terms of their spacings. So I would suggest the same would be for an outdoor bowls. You know, the old people that play the bowls in the white clothing. That'll be me one day. The bowls has to be pretty flat, doesn't it? Otherwise it goes off to the side. Tennis courts have to be pretty flat, and a number of other things have to be quite flat, but yet they still have to drain to the edge. Because if Auckland's getting more like Fiji now, we get our downpours, and you don't want students having to walk through that much water, so it needs to drain as quickly as the rain comes down. So what I'm alluding to is that every type of plan you do will require different contour intervals to get the right. So in my test I've said what would a typical interval for a tennis court be, and you can see to the side 0.05, 50 mils. And I've also set a schematic plan, for example, one of those ones you see on the news with all the colours saying the new motorway proposed from Warkworth to Wellsford or something. So it's over about 20, 30, 40 kilometres, and you don't really want contours down to this much. Every 20 metres is probably fine to show what the hills look like. So you could probably extend that 5, 10, maybe 20 metre contour intervals. So in actual fact, they tend to take their data from aerial photographs, LiDAR, whatever. They don't send surveyors out to the site just for a schematic plan that's going to go on one use. That's tended to be done from existing aerial photography. Whereas when they come to build it, the motorway, then yes, they do need the surveys, and it does need to be done a lot more precisely. For those that don't know anything about motorway design, they have curves on roads, and they have transition curves going into the curves, just so that the cars don't go off the road at 100 kilometres an hour. You're probably driving on the road not even thinking about it, just trying to get the maximum speed out of your car, but all those roads are designed to a speed, and they take into account the inertia, the camber on the road, etc., etc. So designs, motorways, highways, sealed roads, you're going right down to a lot smaller contour interval. And hence there's quite a variety and difference in the type of plan you would produce and the scale you produce it. That chart is also tested in the test. Just a couple of random questions about a couple of those things in there. Contours have various characteristics. For example, if we stayed on the same contour level, a contour, by the way, is an imaginary line that joins up exactly the same height. So if we stayed on the same contour all the way around Auckland, we'd probably go way out towards the city, and then we'd probably go out east and come all the way back again and be exactly the same height above sea level. And therefore, as far as characteristics goes, contours will eventually close on themselves anywhere, as a general rule. But they don't necessarily close on the viewport that you're showing. That's the one thing you're going to have to get to grips with. So you're zooming in on a plan, the contours go off that way and that way, you just have to, in your brain, think, well, they're going to eventually join up and come back again. There is one small thing that I can think of, I don't know, it's probably too predating you guys being born. There was a movie called Cliffhanger with Sylvester Stallone, famous actor that can't talk, and he was hanging from a cliff back in the days when he could. I think he's going to be 70 now. That cliff went down like that, and so it had an undercut on it, and where there's an undercut, contours will cross over themselves. It's the only exception to the rule. Otherwise, generally speaking, contours never cross over. So when you're doing your contours for me, and suddenly they cross over, that's kind of a warning bell that you've done something wrong, all right? Contours, if they are uniformly apart, it means that it's an equal slope either up or down. If the contours come in, they fan in like an arrowhead, that means it's a ridge or a valley. And all these are good little tips if you ever go tramping in New Zealand as well. If the contours are close to each other, stop walking. You could be on the edge of a cliff, or you could be right beside a cliff before you walk up it. We have a number of methods we can use to calculate contours. In the old days, we used to stretch a rubber band between two contour points on a drawing. And before we stretched the rubber band, we would measure out equal intervals, and we'd stretch it and then sellotape it down and mark all those points, and then move it to the next point, and so on. It was the way how we were able to draw our contours from spot heights. Obviously, things have moved on quite a bit from there, so I don't make students do that anymore, but there is the estimation or the eyeball method, and we will do a bit of that today in class here, soon, and we'll do a bit of that this evening on AutoCAD. And it is a bit of a cheats method, but you can get very close to the right contours. Surveyors would be horrified, but at the end of the day, you'll have a weekend in a life. If you don't want a weekend in a life, there is the calculation method which I'll show you on the board here, but it will involve you calculating every single one, which will be good by weekend. Then there's a combo which one student said they did, which was some estimation, some calculation. And then there's something in AutoCAD that I'm going to show you which you might decide to do, most students do, and it's a lot quicker but also accurate. Have I got your attention? Maybe. By the way, there's a circulating list of who's here. Please sign it. If it's stuck there in front of you and you're just going, oh, I wonder what this is, and you put it in your bag, you'll be very popular with the other 70 students in here. Yep, I did get that one year. Everyone was marked absent because these roles go to our administration department, and there was not a single, well, the role didn't make it. Okay, so I'm going to start stepping you through a way of doing an estimation on paper. This isn't on AutoCAD. So for those that have got paper, or even a computer in front of them, and I know you have, I can see these bits of paper everywhere. Why don't you do that on your paper? 100, 97 and 95. So 3 crosses. And I want you to put on the contours from that 99, 98, 97 and 96 contours. And where they fall, just by estimation, along those points. In a couple of minutes, I'll give you another clue. Okay, so let's take a line from 97 to 100 and let's divide that by 3. And another line from 100 to 95 and divide that by 5. And then one from 95 to 97 and divide that by 2. So there's one line in the middle. But who thought about doing that as well? So once you've done the vertical line, you can then join everything up and you end up with something like that. So from 3 points, we've ended up getting eyeballing, of course. It's rough, but it's reasonably accurate. We've managed to get 1, 2, 3, 4 contour lines in there. So that's a very quick and easy method. But what if it wasn't just every metre? What if it was, say, something like that? Let's figure out that one. Okay, so what I'd like you to do is calculate every 0.2 of a metre. So that means not 19.5 and 19.7 and 19.9. That means 18.8, 19.0, 19.2, 19.4, 19.6. So they're the even numbers, and that is what we call 0.2 of a metre contours. So the trick here is that you're required to, it's very hard to do 0.2 straight away, so make it easy on yourself and do 0.1s first. So what I've done here is I've divided it in 0.1s. And then I've gone and just done every 0.2 like that. So I did say that this course requires some lateral thinking, and in this particular case the lateral thinking was to divide every 0.1 and then obviously go back and do things every 0.2. But what if it wasn't as simple as that, and what if you really wanted to spend the weekend doing calculations? Because you've got spot heights all over the place, and you've got to try and, this is called triangulation by the way, when you draw a triangle between the spot heights. And you know, for the surveyors out there who like to do things a little bit more precisely than perhaps the engineers do, in terms of picking up what's on site and etc. What's the calculations behind it all? Well, the surveyors will be pleased to know that it is a little bit like grading, so it can be done on the surveying calculator if you've got one. It can also be done on a scientific calculator if you don't. I might just put a bit of lighting on here, which will kill the board a bit, but hi. Try that. Wow, worked. 44.37, 43.81. So we've got a couple of spot heights here. And we know the distance between them is 20.2 metres. Now in AutoCAD you can measure that distance, just draw a line and list the line, 20.2, right? Or do a dimension if you want to, that's whatever you want to do. So it's reasonably easy to measure a distance between two crosses on AutoCAD. But the next part becomes a little bit harder because you've got to try and calculate exactly where this 44 contour crosses. The way how I do it, and for the first few ones that you do, you'll need to do this, and then after that it'll come in your brain and you won't have to worry about it after that. I have got can guarantee you'll get at least 2 questions like this in the test. Okay? Because you need to know how to calculate where a contour crosses between 2 spotlights. And I'm not going to force you to do it in the assignment, but I'm going to force you to learn the mathematics behind it. Okay? So the way I do it is I draw a profile of this, and I do a triangle, which means the level in the profile view, or a section view. And the level over here, of course, is 43.81. And somewhere over here is going to be where the contour crosses at a level of 44. We know that distance there is 20.2. So breaking it down, we've got a very large triangle. The difference between that and, 8.1, what's the difference between, I will need someone with a calculator here, by the way, who's got one on the front row. Who wants to do the teacher's pet?
56.
56?
0.56.
0.56,
Yeah.
I'm just taking your word for it. I had a degree student who calculated it all completely wrong, which was embarrassing, but okay, so we've got a height difference of 0.56 between these 2 levels, and we've got an overall distance of that. What we're trying to find is this distance x here. So we have another triangle here on the same slope. We've got to find x, but we do know the height difference between 44 and 81, even I can do that, 0.19. So if I was to say to you that the equation was 0.56 divided by 20.2 equals 0.19 divided by x. Is there anyone that doesn't know the maths behind that to solve it? If you don't, can someone do it along the front row? I'm assuming your maths abilities are able to do that.
5.85.
Big one, 5?
6.85. 6.85.
6.85, sorry, it's just me and my hearing bit. Okay, so you get x equals 6.85. It looks about right when you look at it proportionally, so I'll take that as correct. Let's hope you're right. Okay? And that's the simple maths behind calculating between the 2 of them. Now, I have had students that have done spreadsheets, and they've just put the number in, bang, the answers come out, and then they've offset from that point to there, and they've done a little cross or a circle or something on to indicate where it comes through, and then they've just joined up the little circles all the way around with the contours. I have had students that have also calculated it but forgot to put a mark there. That's a no-no. So no triangle lines, no marks, and you won't get your full 2 marks on the contours. Even if you have got a friend who witnessed it and you've got a YouTube video that you did it all perfectly, I will not be giving anyone 2 marks unless they leave their lines on here and some sort of indication of where the calculation came from. I would like you to freeze that in the background, so I only want to see the contour, but then I'll go for the layer that you've got it on. So the layer should be something logical, like triangle, contour mark, something like that, and just freeze it. You can call the layer frozen contour, frozen mark or something. It's up to you. But I'll see it there. I'll thaw it. I'll have a look. I'll put my template on top, and as long as everything's pretty close, you'll be getting marked. Now, everybody's going to end up with different contours, so don't be afraid if your friend's one isn't the same as yours. They'll be close, because I'll do it down here. There's contours, spotlights all around the place, right? Now, you might decide to keep, now there's a saying I've got in engineering, sounds a bit weird, it's called KISS, don't worry, I'm not going to go around kissing everybody. Keep it simple, stupid, which means the most simple way to do it is actually not the stupid way to do it, it's the proper way to do it, okay? So if I was doing this, let me see. Keeping my contours relatively simple, my triangles relatively simple, I should be able to do this something like that. Now I'm not saying it's perfect, but they're simple little triangles and I reckon I could get the contours easy enough. But I've always got my friends that decide, oh no, that's way too easy, let's make life crap. Let's make that my first triangle. Let's come all the way over to here for the next one and then back up to here. Let's do that one and let's now go across to here and up to there and maybe over to this one and up and okay. They should get the same answer, but it will be different and they'll end up with about 5 more contours and it's they'll end up with a lot more markings as well. So keep it simple, stupid. Don't just remember KISS. And I've given an example on Moodle as well, which I'll make available. So this was an example of a couple of years ago, and I just sent this to everybody and said, look, that is what I call very simple triangulation. Yeah, I guess this one here is missed out, but all I did was end up with calculating the points, and I only had to calculate about 3 or 4 for each line, and did it pretty simple. Talking of which, you remember doing something for Ingrid last year where you calculated along a line exactly how far something was, like the bushes or the nodes? Yes. So, instead of doing all this, what if you'd have said, now who was the first one? Someone here said 56 was the difference between there and here, 0.56. Why not divide that by 56? And then count 19 this way, bang, you've got your point. Okay? I know what I'd do, especially where you've got you've got to calculate 4 of them. If you work out the difference between that, and you went up there with nodes, bang. Just count them, mark it, count them, mark it. Maybe do a slightly bigger circle so you know which one to join onto. Freeze them all at the end, and guess what? You'll still get 2 out of 2. Let me turn it on. No problem. The reason why I like to see your calculations is I can check them. I can check some random ones. I've got over 100 assignments with you guys in the degrees to mark. I'm not going to be spending 4 hours on everybody's. That's 400 hours I don't have. So I'm obviously going to go in, thaw it, check a couple of points and get out again. So it's possible you could get and do eyeballing, which would be just going dong, 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 or dong, 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 just approximately, and you might get away with it. I do have a template which is correct, so that'll be my first clue that you've been doing something funny. But my second clue with eyeballing is you've got no nodes there, or circles or anything. So you've just, yeah. So I do catch most, but not all. One student was scribing to me that I'd given him, I don't know why you would email me and say, hey, I got 2 and I did eyeballing, no, but he did last year. And he'd put some nodes on and some off and just gone in between, which was quite clever. And I never picked that up, so yeah. And a lot depends on the time you've got. You know, we had to do a job on the motorway at the moment, the one that's got the tunnel on it, there was a farmer whose farm was being divided in two, and he was arguing that the motorway could have gone anywhere else but his farm. It's been in his family for 6 generations and they're only offering $1 million, and he wanted more, and he was crying about it all. He's crying in our office, and we said we might be able to do some quick design for him just to prove to Transit New Zealand it can be done another way. So we did a quick design for it. We got his lawyers to send Transit New Zealand the design. Transit New Zealand offered him $6 million for the farm, and he went, thanks very much, and ran away. so much for the family farm. And that's the reason for that big bridge that you go under, because it's still one property on both sides. That was the deal that he came. So that's interesting. It was most annoying, actually, because we had to break our drawing down into a big placard that was the size of this room, and we broke it into about 5 panels. To get it up the lift to the Transit New Zealand building at the time, we had to take the piece out of the lift to get it in. It was all printed out on cardboard. We got it all the way to the top, and the lawyer said, oh no, it's all right, we've come to an agreement. We had to take the thing away again. Anyway, sorry, I digress.
Is it the bridge to nowhere on the northern?
Yeah. Well, it was when it went in. That's what it was for. Maybe they've since sold it and divided it. I don't know. Yeah. There's a very similar thing happened on the Clyde Dam. One of the fruit farmers held out. So they sent all the trucks past his farm with the dirt and the dust and everything all over his orchard and everything for 2 years running. He still didn't cave, and in the end he now owns the farm in Cromwell, and he got them to dump the best of topsoil there, and he's had a relocated orchard, which is probably the best one in New Zealand for fruit. So he held out and got a good price. Just shows you, doesn't it? Right, so we've kind of covered the calculations, we've covered nodes, we've covered estimation. I'll do a quick little eyeball thing tonight, but we're moving along to design contours. So we have a platform here, which I'm putting on a slope, and I'm going to show you how, in a very basic format, we calculate design contours using a bit of colour. Now, like everything I do here at Unitec, it's a live demonstration. So there's a bit of, I didn't do a particularly good one for the degrees, hopefully I can improve on that. And it's on a whiteboard compared with if I was to do it on an AutoCAD drawing, I'd be doing it very precise, okay? That said, we do need some sort of form of measurement, so let's do a measuring stick over here. Let's call that roughly 1 metre in terms of horizontal. So that's just my approximate measuring stick, and I'm showing you how to do it. So we've got a platform, we've got to give it some sort of a, let's say it's sitting at 18.0. So we're lowering, let's pretend it was a massive piece of metal, and we're lowering it into a bank. The bank looks like that, and we're putting this platform in like that. Some of it's going to dig into the bank, and some of it's going to come down and be supported by fill. That is fill. So this end here will be fill, and that is what we call cut.
Is there a ratio you require for that slope?
Yeah, we'll get on to that in a second. Good question. But I've done something wrong there, in that I've used dots for my fill hats. Now you will be doing a long section, and we do actually have someone here that works in a lab, geotechnical lab. It wasn't my favourite subject in engineering, but I I do have to tell you that dots means sand, and I think the chances of that standing up in sand are very remote. Don't use dots. So the next thing students do is they use this. They go, oh, that looks good. What a cool hatch that is. Roger will be impressed. Just to show you that I did learn something in geotechnical engineering, that is called rock conglomerate. And you won't be bringing in massive big boulders and rocks from a quarry at a huge cost to Unitech. So please do not use a rock conglomerate hatch. I'm sure you can be inventive in what you use. Okay? For example, something like that might be good enough. And I'm sure you can be inventive on what you use here. That is actually for a building. So if you're sending in a set of drawings that's got buildings hatched like that, and then you do your long section with a hatch like that, it's kind of sending mixed messages. So, yeah. You will need a different type of hatch for cut and fill, so I'll let you come up with something that doesn't conflict with geological terms. So so this platform here will be at 18 metres. I'll do my best to move around so my blooming big carcass isn't on top of everything, but I apologise, at times it can be a little bit hard to see. So yeah, cut and fill. Cut over here and fill over here. So when you're doing design, the first thing you do is recognise that the high ones you're going to cut into the back, the low ones you're going to fill it up. So we'll use red for the next part of the design. Hopefully I've got a good red one. One of these will be good. So as far as cut goes, we are going to use 1-to-1, which incidentally is the same as your assignment. And as far as fill goes, we're going to use 2-to-1. Okay? And I know that a lot of students have not been brought up with things like 1-to-1 and 2-to-1. They've been brought up with angles, and a lot of students end up going, that's an angle of X because of Pythagoras something or other. Well, we're not going to be doing that in my class, so I'm going to play over your head a little bit. We're using grades. Now, interestingly enough, that is actually a very common grade to use in Auckland soils, Auckland clays. It's not always perfectly 1-to-1 or 2-to-1, but it's pretty close. So I'm trying to make the assignment close to what you might be using in real life. So let's do an exercise like that with a 2-to-1 and 1-to-1. Okay? I can tell you there will be some grade questionings in the test, but we will go over some revision on that before we do it. How does the 2-to-1 and 1-to-1 work? Well, it's not that hard to figure out. Every time we go along one, we go up one, and so on. So if we went along 2, we'd go up 2. If we went along 3, we'd go up 3, and so on. On this side, every time we go along 2, we go down 1. So that means if we go along 4, we go down 2. Right. So in this case, looking down in plan view on this, our contour interval is 1 metre, so that means every time we go off 1 metre from here, we're going up 1 metre. So let's look at that division there. Let's start drawing from about here. Let's offset 1 metre. Now I know some of you are going to go, oh, that's bigger than that. Just ignore that at the moment. It's my bad drawing, but I'm doing my best to demonstrate this. So let's come around here and do 1 metre, 1 metre, and 1 metre. So in plan view, we've gone off 1 metre, but we've also gone up in height. Gone up in height by 1 metre as well. So if this platform's 18, this one here is going to be 19, 20, 21, because we've gone along one and up one, along one and up one. 22. We're only doing the cut at the moment. So when we match up the contours, there's the 19. When we match that one up there, there's the 20. We can match the 20 with the 20. 21. 22. Okay, if I was to carry that on, say 23, 24, let's go 24, 25. Eventually we're going to get to a point where we're not touching anything. And I think we've just hit it there. So our 24, which is this one, sorry, that's 23. And 23 touches there. And our 24 touches there. So you can see this is starting to, and our 18 will touch right on the edge of the platform. So you can see that this is starting to form a shape that's sort of something like that. Right? And I can tell you this much of, no, sorry, that line there is going to be called, it's going to be that point there, and we call that the top of cut. Top of cut. None of these lines are needed outside of the cut. Not at all. None at all. Because they are design contours. And they're inside this piece here. What is required outside is these lines here. Because they are existing ground, and if they're outside, the ground doesn't change. But if they're inside, they disappear. Might stop using my finger. Turning everything black back to the desk. Okay. So the existing ground comes in, they form a nice even contour, and then it goes and joins an existing ground again at the other end. Now we can also calculate that on the other side. What tends to happen is this line tends to come round and it'll come back in to this point somewhere around about here. On the fill side of things, we're going along 2 and down 1. So in plan view, we offset 2. 2 is about that much. So let's kind of go around like this. Oh. I'll only do 1 or 2 of these. It's going to go down here at the moment, something like this. Okay. You'll see the fill is probably going to go way over here, way up here, and then back into 18, 17, up here, 16. So it's going to go sort of something like that. And of course, we take off the red that's outside of the wing, and these red lines here are going to go around the corner as well, etc., etc. Now it's more logical that the fill area is going to go further because it's a 2-to-1 slope, and the cut area is going to be smaller. If I was to do this, what does it look like?
Butterfly.
Butterfly, yes. a butterfly flying into the sun, maybe with it shorter on one side. So what students tend to do when they email me is they're saying, I'm having trouble with the top corner of my butterfly wing. And any other person in engineering, any other lecturer would probably go, gee, Roger's using some weird terminology. We don't call it that in industry, so don't go into industry and on your first day say, oh, we're going to be drawing butterflies. It won't work, okay? But using that, and then a lot of, if you email me asking about your butterfly wing, I'll know exactly what you're talking about, okay? Now, we're not finished there. We have a symbol, and I showed you the symbol on week 1 of the symbols that we use for cut and fill. Now, the secret for the symbol, the lines we've drawn, by the way, are these butterfly wings, are that point and that point. The symbol always starts at the top of the bank. So the symbol is going to start there and go down, and there and go down. So our symbol will be on our fill, we'll start on the actual drawing. Now, surveyors have got a double reason to remember this, because when you break off to do your next class, we're doing roads, and your design on the road will be quite different to this. It gets more complicated, so you're going to have to remember where the batter slope is for the fill and where it is for the cut. Now, on the cut, it is actually up here on the actual butterfly wing. So that'll be interesting when you draw that on your proposed plan. By the way, I've just extended that wing as an approximate area. It isn't perfect. And I'll talk a wee bit more about that before we finish up today. But there's a couple more terms I need to tell you. This here is called the toe of fill. The toe of fill. And that would be this point here. Toe of fill. You'll note that a lot of jobs that surveyors get sent out to, there's been a slip, the road slipped away or a building slipped or something. So the first thing that the engineer wants to do is pick up the toe of the slip. So it's in a similar sort of situation. Toe of fill. Now there is another line that we need to preserve. And that is this contour line here. The 18. We need to give it a different line type. Perhaps a dot dot dash dash or something different, included in our key or legend, because this is a very important line. This is called the line of equal cut and fill. Technically, if a digger driver was coming out and he was cutting away this area and filling up that area, the only piece of grass left that you'll see would be this little bit here. Or if they were in clay, the only little bit of original ground would be that line. It also helps determine in plan view where the cut is and where the fill is. Cut is and fill is. So those terms are really important, and a lot of students do the assignment too, and they go, "Hey bro, what's the offset?" "Oh, it's 1 on one side and it's 2 on the other." "Oh, cool. Offset, offset, offset. Yep, I can join the points. I've done it. Is that all?" "Yep." Plan view's worth about 7 or 8 marks. I can't remember how much. And you need all that information on it, plus some more. Talk about that further on down the line. Okay. I've got an AutoCAD example we'll do in the lab tonight. We'll open up an AutoCAD drawing and we'll start trying to plot out the cut and the fill, which will give you a good start towards your assignment. As I said, I'll show you the answer to it. and then I'll show you the answer in 3D, so you can kind of turn that around and look at what things actually look like in 3D. So I'll supply you with that drawing as well. What else? I think there's also a couple of movies that will go with our exercises today as well. Okay, no, that's it. So, are there any questions generally from anybody from the floor? Any student questions? No? Okay. So tonight, just before you go tonight, I'll do a couple of demonstrations. We'll have a little class exercise, and then I'll walk around everybody, give you a couple of questions each, and I can tell you yes or no to how you've done your patching on your wetlands. This is the only week that I'll do that, so make sure you've got it ready for me. Okay. No questions? Yep.
So you said we were going to do that in the test.
Yep, you need to understand the logic of that, because what I do in the test is sometimes I leave that number out, sometimes I leave that number out, sometimes I actually pick up that X, sometimes Y, sometimes another point just past that.
So we need to draw this as well in the test?
No, that will be for assignment 2. Okay, so there's no drawing this year in terms of a test with drawing. You've done that. If you passed it, you can go ahead. I've done like 2,500 students have done previous to you, but yeah, you do have to hand in 4 assignments. That's the challenge. No questions? All right. If you could please pass back the roll if you haven't signed it.